Hi everyone, my name is Xinyu. I'm pleased to present my work Sandwich Bench Normalization, a drop-in replacement for feature distribution heterogeneity, which could be used in multiple tasks. Let's talk about batch normalization first. From the formulation, we can see BM normalizes the input mini-batches of samples by the mean and variance, and then rescales them with nullable affine parameters. In terms of architecture, it is composed of a normalization layer and an affine layer. Later on, categorical conditional batch normalization is proposed based on batch normalization, aiming at supporting conditional information, which is widely used in conditional image generation. Multiple style transfer. It is composed of a normalization layer and a set of independent affine layers. The conditional information controls the activation of affine layers. In our paper, we present sandwich batch normalization. Here's a formulation. It is composed of three parts: a normalization, a sandwich affine, and a set of independent affine layers. We first apply it to conditional image generation task. We use SNGAN, AutoGAN, and BGAN as our baselines. For comparison, we will replace CCBN in the generator with the SABN directly. The results are shown in the table here. We could see sandwich batch normalization could effectively boost the generator performance on both Cypherton and ImageNet. The visual results are shown here. SNGAN with SABN could obtain more visual appealing results. So why does sandwich batch normalization work? Generally, it provides a variable inductive bias for optimization. First, it provides balanced gradient norms, as we can see from this figure here. And second, it preserves diverse gradient directions, and this can be demonstrated in this figure. We could also observe the optimization benefits of SABN in the figure here, where SMBN consistently reduces generator loss and improves in inception score during training. Then we show the application of sandwich batch normalization on the task of neural architecture search. We directly replace BN with SABN in DARTS, a famous differentiable architecture search framework. We could see SABN could help to improve the final search performance in the table here. And then we investigate the effect of the SABN on the adversary robustness task. For this task, we present a new variant, sandwich auxiliary batch normalization, which has independent normalization layers as well, which is modified from the previous successful normalization module, auxiliary batch normalization, and designed for adversary robustness task. The result of the sandwich auxiliary BN is presented in the table here. We could see that the proposed sandwich auxiliary BN is able to consistently improve model standard testing accuracy as well as the robust testing accuracy. We then take a look at the last application of sandwich batch normalization, the arbitrary neural star transfer. We present a new variant for this task, sandwich adaptive instance normalization, which injects a shared affine layer into adaptive instance normalization, which could be seen in the formulation here. The training loss and validation loss of star transfer are presented here. We could observe that sandwich adaptive instance normalization effectively reduces style loss and content loss. The visual results of style transfer are shown in the figure here. Compared to other normalization methods, sandwich batch normalization generates more visual appealing images. Thanks for the listening.